we just read the question for 2A, so the question is there. Hopefully if you are proceeding further you have already solved it, so let us see. Right, it is a through thickness crack, so it is 2A, so A is 79.5 millimeter. We have to find the GC, which is the unknown. The fracture stress is 100 megapascal. The yield strength is 500 megapascal. The E is 207 gigapascal, right? So very simple. K1C is Y sigma F root pi AC. You assume that Y is equal to 1. You write that in the assumptions. Sigma F is 100 megapascal, pi under root, right, 79.5 10 raised to minus 3. You find that K1C is 49.98 megapascal root meter. You know from the chapter, from wherever, that GC, the critical energy release rate, is K1C squared upon E, right? So very simple. You find the K1C square of that by 207,000, because if it is in megapascal and this is giga, so this is 207,000 mega, right? And you just find this value. So the direct answer is so much megajoule per meter square, because it is in mega, but you multiplied by, right, 1000, it will become kilojoule. So it is 12.07 kilojoule per mega square. Remember, don't write megapascal as the unit, right? Megapascal is the same thing, but we have told you that it is joule per square meter, energy per unit surface area. So the unit is very, even if your answer is right, if your unit is wrong, I always want to give a -half there, right? Not to punish you, but for two things. One, that you must remember every time that the correct units are very important. Second, compare it to the other students who have done the very correct unit. So compared to them, yes, your whole other solution is full marks, but this -half for the so this was a very simple question, right? This was again like a gift part. Let's go to the second part of question 2. Question 2B. You have a typical linear elastic material with a rising R curve. One test is performed on a wide plate with a through crack. Another test is performed on a DCB, a specimen of the same material, right? DCB, remember. Both tests are conducted in load control. Would the G values, the G energy release rate, at instability be the same? If not, which geometry would result in a higher value of G? Explain clearly with the help of a rough graph. So again, in the book, you have a flat R curve and a rising R curve. Both those graphs are given. Both those graphs are already given. The only thing for you to decide is that wide plate with a through crack and double cantilever beam, what is the difference between them, and then you show it on the graph. So do it once again, and once you are satisfied with your results, then come back and proceed. So you see, you have this, you have this side with this rising R curve. So this is already there, right? Not these two lines, only that this is crack size, this is G or R, and on this, because it is a rising R curve, so it is a curve. So this much is given. Now the driving force curve G for through crack is linear. Driving for the through crack is linear, while if you look at the equation, G varies with A square for the DCB specimen. So this is the only thing that you want to, you should know it already, but you can just flip a few pages where this discussion is there, and you will come back to know that the G equation is linear for a through crack, and the G equation is proportional to A square, which is a curve. So done, that is done. Now you start with here, make a straight line which will become tangent to this, right? Make a straight line which will become tangent to it. So this is the line for the through crack, and make a curve, a rising curve, right? Not the other, not a decreasing slope. an increasing slope, right? So an increasing slope goes like this. A decreasing slope will go like this, right? So make an increasing slope which will also be tangent at some point. So this is the DCB specimen because it is non-linear. Now once you have done that, then the tangent point is the GC. So right, for the linear one, for the through crack, this is the GC, and for the double cantilever beam, this is the GC. So now this is very clear that the critical energy release rate for the through crack will be much higher, significantly higher than that for the DCB specimen, right? So this is again one of those questions where we have discussed this. We look at the physics of the problem, we look at the math of the problem. You don't have to do any numerical calculation. You don't have to do any numerical calculation. It just, refers to your understanding of the problem, that this graph of the rising R curve is there. Remove the other things from there. Remove the other things. Only the rising R curve graph. And then look at the G equation for a through crack plate with wide crack, and look at the DCB. One is linear, the other is non-linear, and the solution is there. So very elegant solution. Elegant, right? Elegant means that this is not too lengthy and this and this. Very simple. But if this is the right, if this is the rising R curve, if this is the linear line, if this is the non-linear line, then this is one value, this is the other value. We know it is a tangent, and you are done with the solution, right? So this was quiz 3. So now let us move to the last part of the tutorial, which is quiz 4, right? The last part. And again, we will start with the multiple choice and so on. So multiple choice. Wells proposed approximate analysis that related CTOD to K1 for dash yielding. A small scale, medium scale, larger scale, 0. So of course, right, a small scale yielding. That it is elastic plastic, right? So you are just below, just above the yield point, not significantly ductile, otherwise the theory will not be right. A small scale yielding. Based on Irwin's theory, CTOD can be estimated by solving for dash at actual crack tip, displacement, stress, strain, any of these. So if you remember, based on the Irwin theory, CTOD is a displacement, right? It is the opening of the crack tip, So even if you don't know, then you know that you have to solve for displacement. You can't solve for the other thing. This is simply solution of displacement in the equation. Condition to be met for CTOD is equal to K1 square, sorry for my typing, K1 square upon sigma YSE, right? To be true, this is sigma YS, right? Is dash this, right? So all of these through crack, infinite plate, remote stress much smaller than sigma Y. So one condition is that it should be a through crack. Another condition that it should be an infinite plate. And another condition is that the remote stress should be much smaller than sigma ys. So, right, so all three are needed. This is the condition. Rice defined CTOD as 90-degree intercept, displacement at original crack tip, size of the blunting, any of these. So if you remember, it's good. If you don't, just go to the CTOD chapter and see where is Rice, and you will see that 90-degree intercept. Remember, 90-degree intercept. There is a small sketch also for there in the book and the notes. Elastic plastic and non-linear elastic materials have dash loading curves. Same, totally different, slightly different, moderately different. What is your answer? Same. You see, elastic plastic is standard. Linear elastic and then curved plastic. Non-linear elastic is totally curved, right? But when you are loading, it is the same. When you unload, then in the elastic plastic, you draw a line which is parallel to the original straight line. But when it is the non-linear elastic, you go on the same curve. right? So unloading will be different for the two, but loading is the same. So that is the answer. Let's move to the true false part, right? Plastic deformation can be described as time independent non-linear material behavior. What do you think? Time independent? It is not dependent on time, but it is non-linear material behavior. So yes, it is true. High toughness in metals is not desirable to designers and fabricators because K1C measurement of tough materials is difficult. Yes or no? We are confusing you. See, how do we select a material? Based on the property, not because the measurement of the property is easy or difficult. So high toughness should be very desirable, whether measurement of K1C is easy or not. So the answer is false, right? We are saying high toughness is not desirable. No. High toughness is always desirable whenever we make structures from metals in general. Degree of crack blunting increases in proportion to toughness of the metal. What is your answer? It should be obvious. Yes, right? Because if the toughness is high, it means it is more ductile. So there will be more blunting of the crack. A strip yield model assumes plane strain conditions and a non-hardening material. Because there are only one model, the other model, right? This is the Griffith model, this is the strip yield model. So you should remember it. But if you don't, again, the book is open. So your answer is false. False, right? Plane stress and so on. Crack tip conditions in elastic plastic materials are described by CTOD or J. What do you think? We are not talking of linear elastic because now we are talking of CTOD or J. So these are the elastic plastic constants. So yes, this is very true. Just like in linear elastic materials, it is K1 or G, right? K1 or G. So here it is CTOD or J. So we have again finished the part where we are doing the multiple choice or the true false. Some examples, of course. I mean, in the actual example, I have prepared many more, and it comes by shuffling to you. So each one of you can get a few other questions also. So you need to be prepared. Question 2A of this quiz. Very simple again, right? Very simple, but simple if you have gone through this chapter. A flat plate is made from a steel having a fracture toughness of 50 megapascal root meter, yield strength of 500 megapascal, and elastic modulus of 207 gigapascal. So all the material values are given. A, find the value of the critical energy release rate, GC. B, using Wells theory for a small scale yielding, determine the critical value of the crack tip opening displacement, CTOD, based on Wells theory. C, taking alpha is equal to 1 and assuming that the reference stress is the yield strength, find the critical value of J integral under plane stress conditions for a material having a hardening parameter of 4, small n, right? So these are given, and the chapter is EPFM, elastic plastic fracture mechanics, and this area where the Wells theory is there and the hardening parameter curve is there, just go there, use it, solve it, don't go further. First completely solve it. Once you have done the solution, then return back and compare.